Hello everyone, I'm third year PhD student from Royce Institute, Department of Material. Today I'm talking about developing application of low carbon cement. I'm starting from a general broader concept, what's a low carbon cement, and what's the advantage of it, what's the limitation of it, to my specific research, what my research can do, what my research is expected to contribute to developing low carbon cement. First of all, this is a background. Cement is everywhere in our life. We cannot live without cement. This building is constructed by cement. But a critical problem we need to realize is cement and concrete industry takes up 8% global carbon emission. It can be ignored. And in addition to this, since 1960s to now 60 years, there has been a continuous increasing in terms of the cement production. And it's predicted that in the next 3 decades, it will continue going up, especially for the developing country. So it's imminent to solve this issue, to cut off the global carbon emission of cement and concrete industry. So, who is the main contributor to cement and the concrete industry in terms of the carbon emission? And who is the criminal? Clinker. What's a clinker? Clinker is a raw material to produce cement. The main composition of clinker is calcium oxide. If we want to produce clinker, it's necessary for the calcination of limestone and the clay, which are both fossil fuel. By this process, it will emit a lot of carbon dioxide. Moreover, this process requires a large energy cost. As you can see the right figures, even clinker only takes up lower 10% proportion in final concrete production, but it emits about 90% carbon emission, total carbon emission. So what we can do to cut off the carbon emission in cement and the concrete industry. From raw material to final construction, there are 4 parts. The first is from raw material to cement. The second part is from the cement to concrete. And the final part is from concrete to construction. The cement is a binder, is a glue for gluing the construction material. And if we want to produce a general Portland cement, we need to mix the clinker and water. We produce a cement. After that, we add some aggregate into the cement. We have the concrete. From clinker aspect, what we can do, if we can cut off the carbon dioxide emission from clinker, this part, of course, we can cut a lot of carbon dioxide emission. The first solution is we will think if we can decrease the proportion of clinker to produce a cement. Yes, we can. A lot of people is doing this thing. But the second way is use sustainable additive ingredient to produce cement, replace the clinker, replace the raw material. This is the topic, circular economy in cement industry. And by this way, alkaline activated cement is this kind of cement by using the sustainable alternative ingredient to produce a cement. It's produced by mixture of the alkaline activator and some precursor to produce a cement. There are much more sources in terms of the precursor. It can be from anyway, with industry byproduct like slag or fly ash. which are both the ions byproduct from iron and steel industry. We can use this waste, industrial waste, to produce a cement. By this way, we can cut off the carbon emissions. As you can see, this is the advantage of alkaline activated cement. It reduces a lot of carbon emission compared with conventional Portland cement. Also, and it saves a lot of energy cost. The advantage of the alkaline activated cement is high strength, especially by using sodium silicate activator to produce the alkaline activated cement. As you can see, even the strength, the alkaline activated slag cement produced by sodium silicate activator, the strength development is comparable, even better than conventional Portland cement. For other activators, even they have a slower stress development. It's not qualified for final construction for building using, but it's also promising. But why? Since 1970, 50 years, the first alkaline activated cement was used for construction. Why? Up to now, it cannot be large scale used for the construction building material because there are a lot of limitations, like high cost, environmental impact, and dry shrinkage. High cost, especially for sodium silicate and sodium hydroxide activated cement, because the activator is a strong alkaline activator solution. They are very expensive. And the second limitation is the environmental impact, because sodium silicate and sodium hydroxide are both strong alkaline. They will bring the environmental pollution. It cannot be avoided. And the shrinkage problem. What's the shrinkage? Shrinkage is a property of cement. When it has this property, it cannot be adapted to the low humidity environment. These factors limited the alkaline activated cement. And also, complete chemistry and mineralogy of the alkaline activated cement limited their application. Because we don't know, we just know what they are, what's the performance they have, but we don't know why. We don't know what kind of mechanism lead this performance of them. And the supply chain difficulty, because like limestone and the clay, they are everywhere. They're from fuel fossil, but like slag or fly ash, they are not everywhere. Just a limited region, limited country have. So this is a problem. We cannot standardize the production of the alkaline activated cement. So the key to develop the alkaline activated cement for future practical using to large scale produce it is developing the alkaline activated slag cement with a none or less strong alkaline activator, using but qualified performance. As I said, sodium silicate and sodium hydroxide, they have both strong alkalinity, but the side effect is also significant, like environmental pollution, like handle risk. Is not easy for operator to produce cement by operating the strong alkaline solution, and the cost is very high. Incidentally, sodium carbonate and sodium sulfite are near neutron source, near neutron activator to produce alkaline activated cement. They are both environment friendly, less pollution, low risk, and low cost because they are nature abundant. But the main problem of them are the low stress development. The reaction of these two activators cement is low. The mechanical performance, the strength is not satisfied. So my project, my PhD, my ambitions is figure out the whole relationship from the activator chemistry, how activator chemistry influences the chemical reaction and influences the cement mineralogy, and how cement mineralogy influences the microstructure of the cement and how microstructure influences the mechanical performance, especially focusing on the microstructure part, how cement mineralogy influences microstructure, and what's the inner relationship between the microstructure to mechanical performance. Once we figure out the inner relationship of the alkaline activity cement, not only we can contribute to the knowledge base of this material, but also we are promising to directionally decide the alkaline activity cement with qualified performance and also maintain environment-friendly requirement. So, my PhD is focusing on using X-ray tomography to study the microstructure of cement. This is X-ray CT. CT scan is always using in clinical medical area, but it's a powerful tool. It's also a powerful tool for material study. What it can do, like a small piece of cement, we can scan. We can use micro X-ray tomography to scan it, and we can know the microstructure of it. We can know the porosity. We can know where this pores, and we can know, oh, there is a crack, and even we can know, oh, what kind of phase it formed. This is my part result from my study. I'm using X-ray tomography to learn the dynamic change of the cement, alkaline activity cement during different curing age. And for cement material, the longer curing age, ideally, the better strength it has. So by this research, I answered the question. I was curious is why the sodium silicate and the sodium hydroxide are both strong alkalinity activated, but sodium hydroxide, the strength development is slower than sodium silicate. Even the alkalinity of the sodium hydroxide is better than the sodium silicate. This is a question, long-term question in this area. By using X-ray CT quantitative analysis, we know the left figure I'm showing the reaction rate. The reaction rate is a linear proportional to the alkalinity of the three cement. And the right figure shows the pore structure. The tutorosity, the larger value represents the more homogeneous the microstructure, the more disconnected pore structure. So maybe from this aspect, this is the reason why sodium silicate activated cement material has a better performance in terms of the stress development. But once we know this, we can, from pore structure and microstructure aspect, to inversely decide what we want to get in later cement design. And this is another study. This study, I'm evaluating the durability, because for cement material, in addition to the strength, we also care about the durability, how long it can be conserved, how long is its life. Maybe 50 years or 100 years or even longer. But for alkaline activity material, it only has a 50 years history, so it's very difficult. It's very hard to see what was the durability performance of that. So this study, I evaluated the activator influence the microstructure during some corrosion test, because the main reason induced the degradation of the cement is the reaction between the cement piece and the sodium with the carbon dioxide, chloride, and the sodium sulfite. This corrosive gas will will degrade the cement microstructure. This study, I evaluated the sodium carbonate activated cement have a weaker durability than the sodium silicate cement. Yeah. This is a very interesting point. In later cement study, we can figure out why the microstructure perform like this. So we can enhance, we can improve the performance of the sodium carbonate activated cement for future using. Thank you.
Questions? Veronica, you're first.
Yeah, that was very, very interesting actually. So you studied all the degradation against some gases. I come from a country where it's very, very, very hot in summer. And I was wondering if you have done actually a study of degradation with temperature. Imagine this cement to be used across different countries.
Temperature, yeah. It's not my focus, but I have some project get involved to study the performance of the cement in service in different temperature. Ideally, for cement material, when it is used in high temperature environment, the good thing is it reacts faster, which means the stress development is faster. We can achieve the higher stress of the cement material by a shorter time. But the side effect is the evaporation. The higher temperature will lead to the evaporation of the cement solution of the cement, which means it's easy to initiate some crack. So maybe will damage the in-service life of the cement. Yeah.
We have time.
Yeah.
I was wondering around, you kind of talked about environmental impacts and the carbon emissions associated with that. From Nicholas's and Lois's kind of presentations, we saw that environmental impact isn't just the carbon emissions. So I was wondering if you'd had a look at any of the other environmental impacts from this process.
Yes, like the pollution, like I said, the alkaline pollution. Because the main limitation limited why alkaline activated cement for large-scale production, large-scale using is because of the strong alkalinity will lead to some pollution, environmental pollution. And also there is another environmental factor like energy cost. Actually, as I mentioned, for produce a unit weight of this alkaline activated cement, the energy cost is much lower than the conventional Portland cement. But the problem is the cost is much higher. Yeah.
Thank you.
Save it for the panel. So please join me in thanking all of our speakers.